the last class we discussed about fixed bias scheme and saw that this biasing scheme is highly sensitive to variation of beta. So, if beta changes, then the operating point will shift. Now, let us discuss some other scheme of biasing where this effect of change of beta on the operating point can be countered by designing the biasing scheme parameters specifically. So, one method of biasing which will be now discussed is emitter bias. So, in emitter bias scheme there is a resistance in the emitter, that is Re. This resistance in the emitter serves one particular purpose that we will be discussing, but the difference between the fixed bias and this emitter bias scheme is that we have a resistance in the emitter circuit. Emitter to ground has a resistance Re. So, in this scheme, if we now find out what will be the base current IB, applying the Kirchhoff's voltage law again in the loop from VCC, if we travel to ground through the base, then we get VCC minus this drop which is IE into Re minus IB into RB is equal to 0. So, VCC minus IB RB minus of course base to emitter voltage drop we have to consider. So, we cannot forget that, minus VBE minus this drop IRE equal to 0. This is the Kirchhoff's voltage law in this loop. So, now if we express this emitter current IE is equal to beta plus 1 IB, then we get the expression for the base current equal to VCC minus VBE divided by RB plus beta plus 1 into RE. And so, the collector current IC can be found out after finding out this IB, we can multiply IB by beta and we get the collector current. Of course, in all these analysis we are ignoring the leakage current or reverse saturation current because it is in the active region. We can very well neglect that reverse saturation current part. So, it is a linear relationship, that is IC is equal to beta times of IB. So, now if you substitute the value of IB from this expression, we get the collector current as beta times this expression of IB which is VCC minus VBE divided by RB plus beta plus 1 RE. So, this is collector current. If we know the collector current, now we can travel from VCC to ground through the collector emitter loop. If we now look into the expression for VCE, so VCE will be VCC minus ICRC minus IERE. So, we can write VCE equal to VCC minus ICRC minus IERE. So, once we know this IC, we substitute this IC here and I is equal to IC plus IB, IB is already known. So, we can find out the operating point. Now, one important thing here is the inclusion of this resistance in the emitter serves one special purpose of self biasing. This circuit is also known as self bias. So, that self biasing can be understood. Now, if we see the consequence of increase of the collector current due to temperature increase. Suppose the temperature is increased, then as temperature increased, the reverse saturation current IC naught will be rising. So, IC naught rises means the collector current IC will rise. So, as a result of this, the operating point will shift, because rise of collector current means your operating point will shift towards the saturation region from the earlier operating point. So, now if this shifting occurs, then our biasing scheme whatever we have designed will not now be valid, because we have a different operating point now, shifted operating point. Now, to counter effect that is taken care of by this emitter resistance, because if we now have a rise of IC because of rise of IC naught, what will happen? This drop across this emitter resistance will be rising, because this resistance drop is what? IE into RE. So, IE into RE will be increasing because of increment of IC. So, as this drop increases, the current in the base, that is the base current, which is equal to nothing but VCC minus IRE divided by VCC minus VBE minus IRE divided by RB, that is the base current. Now, if we have a rise of IC, correspondingly IE will rise, and so this drop IRE will rise. So, as it is having a negative sign, so increment of IRE means the whole numerator quantity will be decreased. As a result, that means we are having now IB lesser. Whatever increment has taken place in the IC, that will be balanced, because of this increment of IC resulting in the numerator quantity being decreased. So, IB will be again coming down, and coming down of IB will be in fact causing IC to bring down, it will be bringing the IC down, because beta times of IB is equal to IC. So, if you have IB brought down, then IC will be also brought down. That means, whatever increment of IC has taken place due to increment of temperature because of rise of the saturation current, this effect again brought the IB back, because of this drop being increased across this resistance, that in fact again brought down the collector current. So, whatever effect was there because of rise of IC, that is counterbalanced by this method of self biasing. So, that is why it is called self biasing. So, this scheme is better than the fixed bias scheme in this sense. And if even beta changes because of say replacement of the transistor during operation by another transistor which has a different beta, then we see here in this expression that IC is equal to VCC minus VBE into beta by this expression in the denominator, which is RB plus beta plus 1 RE. Now, as this IC is sensitive to beta variation, because beta is sitting both in the numerator and denominator. So, if beta changes, obviously IC will change, but if we see the expression of IC carefully and maintain one particular criterion, that the resistance RB, if it is very less than beta plus 1 RE term, that can be designed accordingly. While designing the biasing scheme, we can design in such a way that if we make the value of the base resistance very smaller than the whole expression of beta plus 1 into RE, then we can write down this expression approximately as VCC minus VB into beta divided by this whole summation. If this term is very small than this term, we can approximately write the whole denominator term as beta plus 1 RE, because in comparison with RB this factor is quite large if the design is done like that. So, we can write beta plus 1 RE, and beta plus 1 values are almost equal, because beta is a high value. Suppose beta is 100 and 101, it can be assumed to be equal. So, beta and beta plus 1 can be cancelled out. So, in this expression of IC now, we will be left with final expression VCC minus VBE by RE, which is getting rid of that term beta, and that is what is the aim of our design, because we should get rid of the term beta in the expression for IC, since beta variation will not then affect the IC will not vary with beta. So, finally, in this expression of IC we see that VCC minus VBE, VBE is the drop, constant drop of 0.7 volt for silicon, VCC is a constant biasing voltage that we apply, and RE, once we designed RE we are not going to change it. So, this whole expression is now the expression for IC, and so it is not affected by beta. So, IC is independent of beta if we maintain this particular design criterion. So, under this condition only IC will be independent of beta. So, as long as this condition holds, that we have designed the values of RB and RE in such a way that for that particular transistor with a particular value of beta, this condition is maintained, then we get almost constant biasing scheme. I mean, it is not, the collector current will not vary with beta, that means we are getting an operating point which is stabilized. So, this scheme is better than the fixed bias scheme. Another scheme is there which is collector feedback bias. So, in the collector feedback bias, this collector is having a feedback resistance which is connected to base. That means, there is this feedback loop from collector to base through this resistance RB. So, here this is the biasing scheme along with the signal when you apply for this amplifier, common emitter amplifier. Here the input signal we apply at the input between this point and the ground, and AC input signal we want to amplify. So, at the collector point with respect to ground, we are expecting an amplified signal without distortion at the output, that is the AC output signal. The presence of these capacitances C1 and C2 are to couple the signal effectively, and under DC condition when we only discuss the biasing scheme, these capacitances are open circuiting, because under DC condition capacitance offers infinite capacitive reactance. So, it is almost open circuit. That is why in the DC equivalent circuit for this whole amplifier, if we draw, we will be left with the circuit which is shown here. Here we are not having this capacitance as C1 and C2, and the others are RC, RB are there, and here we are not we are having a scheme for a biasing which is not having a resistance in the emitter. So, first of all we are only having the capacitor to base biasing resistance RB, and there is no resistance in the emitter. So, this is a different scheme of biasing which is known as collector feedback bias scheme. So, in this collector feedback biasing scheme, now if we analyze this circuit and find out what will be the base current, what will be the collector current, correspondingly what will be the collector to emitter voltage, that will define the operating point, because operating point is defined by the DC collector current and collector to emitter DC voltage. So, we need to find out for this biasing scheme what is the collector current, what is the collector to emitter voltage, in order to know the operating point Q, which is known as quiescent point or silent point, means without any signal when we first find out the DC condition. When you apply the signal for amplification, then of course, we will have to analyze it in a different way, drawing the AC equivalent circuit, and that we will be taking up later. So, for the time being, now let us find out what will be the IC current, what will be BCE. So, for this equivalent circuit, the currents as shown, the current through this RC will be IC plus IB, because here this base current is flowing into the base and the emitter current is IB plus IC, that is the emitter current. The current which is flowing into the transistor must be the same emitter current, because that is the current which is outgoing from the transistor. So, in order to validly follow the loop, the incoming current into this transistor must be equal to the outgoing current, because that is, if we consider this collector to emitter to ground circuit differently, I mean in a separate separately if we consider, then we can write down this, we can see this whole this circuit, because VCC is having positive and negative terminal. Positive will be here and this is negative, this is ground. So, the current which is coming out from the positive terminal of the source must be the same current which will be flowing into the negative terminal. The current which is this current, that is the current which is through this resistance RC, has to be then definitely the same I current, IC plus IB, because this current is I. So, this completes this outgoing current from the source and in entering current into the source. So, that two are equal. So, that is why the current which is seen here is IC plus IB, or that is equal to IE. One part of this current will flow to the base, that is the base current. The other part will be flowing into the collector, and then this collector current and this base current will meet in the emitter, that will be together flowing, that is summation of this collector and base current, that is equal to the emitter current. So, now if we find out the collector current, then we must first find out the base current, and then we will be finding out by multiplying it with beta. So, what is the base current? So, in order to know the base current, then we have to follow the travel from VCC through RB through base to ground, apply Kirchhoff's voltage law. If we apply Kirchhoff's voltage law, then from this point, it is of course positive point of the VCC, and it will be VCC minus this drop, which is equal to IC plus IB into RC, minus this drop, which is equal to IB into RB, minus VBE, base to emitter voltage, that is equal to 0, because this point emitter and ground, that is the same point, we are not having any resistance there. So, this is at ground potential, emitter is ground potential. So, now we can further simplify this expression by putting IC equal to beta times of IB. I want to find the expression in terms of IB, because then we can easily find out what is the value of IB. So, whatever I see, I can write it as beta times of IB, and then I have the unknown which is IB only. So, now we get the expression as beta plus VCC minus beta plus 1 into IB into RC minus IB into RB minus VBE is equal to 0, or we can further simplify it by writing it as VCC minus RB plus beta plus 1 into RC whole into IB, taking IB common between this term and this term, I am getting this expression minus VBE is equal to 0. So, now I can very easily find out what is the value of beta IB. What is the value of IB? That IB is equal to VCC minus VBE divided by RB plus beta plus 1 into RC. So, this expression of IB now will lead towards finding out IC by simply multiplying IB by beta. So, beta times this expression VCC minus VB by whole denominator, that is RB plus beta plus 1 into RC, this is my IC now. So, I have found out the value of IC by putting the values of corresponding resistances and whatever the value of beta for that particular transistor what we are using, as well as the applied biasing voltage VCC, because here one voltage source is used, that is VCC, and we can easily find out the value of IC. Now, what is the value of collector to emitter voltage, that is required to be known. So, VCE can be found out if I travel from VCC towards ground through the collector emitter part. So, starting from this point, VCC minus IC plus IB into RC minus VCE equal to 0. So, that is the Kirchhoff's voltage law in this output circuit, that is VCC minus IC plus IB into RC minus VCE equal to 0. So, from here I can find out what is VCE. VCE is equal to VCC minus IC plus IB into RC. So, now we are having the operating point defined by IC and VCE. Having known the operating point, now let us see whether the bias stabilization is satisfied here or not, meaning the change of beta will affect the collector current in what way. Here we are considering change of beta, which is actually more prominent than the other changes which may also occur, like your temperature change, but we are considering beta change which has a dominating effect on this change of IC, correspondingly the shifting of the operating point Q. So, let us find out how the change of beta is going to affect the collector current. In this expression, it is very clear that beta is there in both the numerator and denominator for this expression for IC. So, definitely it is very sensitive to beta variation. Now, if we now can design the biasing scheme in such a way that we can have the expression for IC getting rid of the term beta in the limiting condition of some limiting design specification being met, then we can achieve that. So, for that intuitively we can see that in the denominator of this IC expression we are having RB plus beta plus 1 RC. So, likewise as we have done in earlier, we have seen in emitter bias configuration, if we now can make the value of RB to be very small in comparison with the other term in the denominator, that is beta plus 1 RC, then we can write this whole expression as having in the denominator beta plus 1 RC. So, that is actually possible. If RB is very less than beta plus 1 RC, then we can write the expression for IC as VCC minus VBE into beta by beta plus 1 RC, and then we can cancel beta and beta plus 1 which are nearly equal because beta is a high value, and then we will be getting an expression which is not having beta. So, that is what is obtained here. Finally, if this condition is met, that is RB is very less than beta plus 1 RC, then we can get that IC is equal to approximately, of course exact expression it is not so, but after satisfying this design criterion we can write approximately IC equal to VCC minus VBE by RC, and here it is independent of beta. So, that means we are making this IC independent of beta after meeting the design specification in this way. So, this is a key expression or the key design condition we have to meet while designing this biasing scheme, and then we can achieve that IC being insensitive to beta. This collector feedback bias can be combined with actually the emitter bias which we discussed earlier in order to give a biasing scheme which is emitter and collector feedback bias scheme. Here collector feedback resistance is there which is RB, collector to base resistance, and this emitter is also having a resistance. So, basically it is this this scheme is having both the aspects of collector feedback bias as well as emitter bias or self bias. So, this is the scheme, biasing scheme, that when you apply to a common emitter transistor amplifier, the whole circuit for this amplifier will be like this. Here we are applying the AC input signal and we will be getting the AC output signal at this point at the output, and now in order to analyze the circuit in the biasing condition or the DC equivalent circuit, we will have to find out, and that is the equivalent DC circuit for this amplifier is this one. So, C1 and C2 being open circuited under DC condition. So, we are getting this collector emitter feedback bias. So, here there is this resistance in the emitter, others are same as the scheme just now discussed, that is the collector feedback bias scheme. So, here also we can find out the insensitivity condition of IC to beta condition. So, first of all, in order to find out what is the collector current, we must find out base current. So, the KVL being applied to the circuit having this collector base loop, we will be applying the KVL in this loop. So, it will be VCC minus IC plus IB into RC minus IB into RB minus VBE minus beta plus 1 IB into RE is equal to 0. So, here we will have to be careful that RE is the resistance in the emitter, it is not simply grounded, it is through a resistance that is grounded. So, we have this equation here, instead of writing IE, it is just written in this way just for easy calculation of IB. We have written down IE is equal to IC plus IB, that is equal to beta plus 1 IB. So, using this we are getting the final expression of IB from these equations after simplification. First step simplification is we have to write down IC is equal to beta times IB. So, all the ICs we will be writing down as beta times of IB, then we get beta times IB plus IB into RC minus IB into RB minus VB minus beta plus 1 IB into RE is equal to 0, or VCC minus taking common IB we get RB plus beta plus 1 into RC plus RE minus VB is equal to 0. So, what we get in the expression for IB is this one, VCC minus VB by RB plus beta plus 1 into RC plus RE. So, instead of the earlier collector feedback bias scheme, if we see, we had here RB plus beta plus 1 RC, but in this scheme RE term will come, RE will be coming in the denominator in extra with RC. So, now if we know IB, we can find out IC by multiplying with beta, and correspondingly we can find out VCE, which is equal to VCC minus this drop minus this drop, that means VCC minus IC plus IB into RC minus IB plus IC into RE. Taking combine IC plus IB, taking it common, we can write this expression. So, this is VCE expression, this is IC. So, we know what will be the Q point, which is defined by IC and VCE. So, now what about the bias stabilization under this circuit? The condition if RB is very less as compared to beta plus 1 into RC plus RE, then we can write approximately IC equal to VCC minus VBE into beta divided by beta plus 1 RC plus RE. So, we can cancel out beta and beta plus 1, and final expression will be IC almost equal to or approximately equal to VCC minus VBE by RC plus RE. So, here we are getting rid of the beta term. So, we have made IC independent of beta provided we maintain this design scheme of making or keeping RB very less as compared to beta plus 1 into RC plus RE. So, you have to design it like this, design the circuit like this, that means keeping in view this criterion till when this is met, only then you can make it, the IC collector current can be made insensitive to beta. Now, finally, we will be discussing a scheme which is most popularly used, having advantages, which is known as voltage divider bias scheme or potential divider bias scheme. In this scheme, apart from using a single resistance RB, there are two resistances R1 and R2 being used in this fashion. others are similar to the earlier schemes, that means RC and RE are there, and we do not have a single RB, but we are having R1 and R2, that is a dividing scheme, potential dividing scheme is like this one is used for this bias scheme, and this is the whole amplifier circuit. Now, in this circuit, if we analyze the DC condition, that means we just open circuit C1 and C2 under DC condition. So, it will be this circuit, which is the DC equivalent circuit for this amplifier. So, here R1, R2 resistances, RC, RE are the resistances in collector and emitter. So, now just for easy analysis, I have just now divided or separated out the resistances R1 and R2 with VCC, and the other is RC and RE. This is also sharing this VCC. So, this scheme is nothing but this scheme only, but I am drawing it just to easily understand the circuit, and this is the bias base point, collector point is here, emitter is here. So, now in this circuit we have to find out base current. Now, what we can do is that we can simplify the circuit, or we can make it more easier for analysis if we concentrate on this base to emitter circuit and try to find its equivalent Thevenin circuit. Then we can easily analyze it, and that will be clear here. If we now look from this AB terminal, from this point you just look into the AB terminal and find out what will be this equivalent circuit by Thevenin's theorem if we replace this VCC R1 R2 by its Thevenin's equivalent at this point. That means, we look into the AB terminals from this side, that means, we are trying to find out the equivalent Thevenin circuit from base to ground, that is from these 2 points we will be looking into and finding out what is the Thevenin's equivalent. So, as we know, Thevenin's equivalent circuit consists of two things, one is the Thevenin's equivalent voltage and the Thevenin's equivalent resistance, that we have to find out first. So, in order to find out Thevenin's equivalent voltage, we have to open circuit these 2 points and find out its open circuit voltage across these 2 points, and in order to find out the Thevenin's equivalent resistance, you kill the independent source VCC, find out the equivalent of these 2 resistances. So, now in order to do that, we will be having to find out what is the Thevenin's equivalent. So, we have this VCC and we have this R1 and R2. So, basically this across these 2 points A and B, the right side of this circuit is having all those base and collector circuits, etc., but then we are finding out Thevenin's equivalent looking from this terminal, this point, that is across A B we are just looking at to find out what is the Thevenin's equivalent. So, Thevenin's equivalent across this Thevenin's equivalent voltage across these 2 points V Thevenin, that can be found out. It is a voltage division provided this base current is ignored. So, if base current is ignored, then only we can find out Thevenin's equivalent like this, because if base current is not ignored, there is a base current flowing, then these IR1 and IR2 will not be equal. Exactly IR1 and IR2 are not equal, but we have conveniently we will be ignoring this base current since its value is very small, and approximately we can replace this whole circuit by its Thevenin's equivalent, provided this IB is ignored, that is it is very small. So, we can neglect it, that means this current and this current are same. If we neglect base current, then we can find out this equivalent. So, here this point is to be noted. So, now if we find out, so this same current should flow. otherwise you cannot find out Thevenin's equivalent in this way. So, what is Thevenin's equivalent voltage across these 2 points? VCC into R2 by R1 plus R2. And while finding out Thevenin's equivalent resistance, we must kill this voltage source, independent source. So, it will be then this one, that is across AB we are finding out what is the equivalent resistance looking from this terminal, that is nothing but you have this point ground it, mind it, this point is ground. So, this is R1 parallel R2, these two nodes, these two resistances are in parallel, R1 parallel R2. That means, it is R1 into R2 by R1 plus R2. So, that is what we get for this circuit to the left of this base A to ground, that means across this AB we are getting this Thevenin's equivalent circuit. So, now we will be replacing easily, replacing this by B Thevenin in series with the R Thevenin resistance. So, the left part is taken care of by this B Thevenin and R Thevenin, and this right side is exactly same, we are not doing anything. So, now it is easier for us to find out the base current in this loop. If we find out the base current, now what will be the base current? This is now the equivalent circuit after replacing the base to ground circuit by its Thevenin's equivalent to the left. So, now if we consider the base emitter loop, B Thevenin minus IB into R Thevenin minus VBE minus IE into RE or beta plus 1 IB into RE is equal to 0. So, now we can find out what is the base current. What is the base current? Base current equal to V Thevenin minus VBE by R Thevenin plus beta plus 1 into RE. This is the expression for IB finally. So, once we know IB, we can find out IC. IC is equal to beta times of IB. So, beta times into this whole expression. And what is the collector to emitter voltage VCE? Again we have to go by this loop, apply KVL, VCC minus IC into RC minus this drop which is IE into RE. So, that is equal to VCE. So, VCE equal to then VCC minus IC into RC minus IC plus IB into RE also you can write, or you can directly write beta plus 1 into IB into RE. And what is IC? We have already found out, and we can also find out by writing it beta times of IB. So, finally, we get VCE and we get IC. This determines the operating point or the quiescent point. Now, the bias stabilization can be done, or the IC current can be made insensitive to beta if the denominator term R Thevenin, that is the resistance, Thevenin's equivalent resistance can be made very small as compared to beta plus 1 RE. So, then this expression will be boiling down to IC is almost equal to B Thevenin minus VB by RE, because beta by beta plus 1 will cancel, since we are writing R Thevenin plus beta plus 1 into RE approximately equal to beta plus 1 into RE, ignoring this R Thevenin since it is very less than whole term beta plus 1 into RE. And beta V Thevenin and R Thevenin we can calculate, we already know, which is beta V Thevenin VCC into R2 by R1 plus R2, R Thevenin we know R1 parallel R2. So, now we have made IC insensitive to beta, which will be equal to V Thevenin minus VBE by RE. So, there is no beta here. So, it is made independent of beta by choosing this properly. These resistances should be chosen properly. And here one thing is to be noted that since we are having two resistances R1 and R2, we can very well find that combination of R1 and R2, the values being small, of course, R1 and R2 will be small, and their parallel combination of R1 and R2 will be still smaller. So, that can be made small in comparison with beta plus 1 RE, and it is more flexible in the sense that when we had only RB, one resistance in earlier cases, then to make RB very small, it was difficult, because other criterion will also be there. You cannot have RB very small, because IB will be also increasing, and there is a limiting condition for every transistor, which is very much specified in the data sheets, what will be the limiting conditions, limiting power, etc. So, actually we are not free to choose any value, but within the limitations we can choose better values to make this happen, that this condition to be satisfied, and it is better to have two resistances R1 and R2. When we choose, we can very well choose the combination in order to meet this specification than deciding on a single resistance RB that was done earlier. So, now let us try one example. In this potential divider circuit biasing scheme, we have to find out the change in the collector current IC when beta changes from 100 to 300. That is, we have one case beta is 100 and the other case beta is 300. So, what will be the change in the current IC that we have to see. So, in this circuit, the potential divider biasing scheme has the resistances as 8K R1, then RC is 4.7K, this is VCC is 10 volt, and this is the transistor, and this is an NPN transistor, and this resistance RE is 1.2 K and this R2 is 2 K. So, this is ground. So, now I can first of all, and beta is also given, which value is changing, actually one is 100 first case, another is 300. So, now I can very well approximately I will be first drawing the equivalent circuit using Thevenin's. So, this whole circuit can be written down as the circuit using that Thevenin's equivalent like this. So, you have this is VCC, VCC is 10 volt, RC is 4.7 kilo ohm, R Thevenin and V Thevenin we have to find out. RE is given as 1.2 kilo ohm. So, now what is V Thevenin? That is equal to VCC into R2 by R1 plus R2. So, here we see that what is, if we look from this base, this is collector, this is emitter. So, you have to look from base to ground, these 2 points, you look to the circuit to the left. I want to find out across these 2 points. So, VCC into R2 by R1 plus R2, and that is equal to 10 into R2 is equal to 2, R2 is 2 kilo ohm, 2 by 2 plus 8, 10. So, it comes to 10 into 10 cancel, 2 volt. V Thevenin is 2 volt and R Thevenin is R1 plus R2, that is R1 R2 by R1 plus R2. So, multiplying this 2 and 8, 8 and 2 by 8, 8 into 2 by 8 plus 2. So, 16 by 10, 1.6 K. So, I get 1.6 K R Thevenin and I get 2 volt as V Thevenin. So, now this is the base current IB, this is the collector current IC, this is the emitter current. So, I will be finding out IB. So, IB is equal to V Thevenin minus VBE by RB plus beta plus 1 RE. Putting down these values here, V Thevenin we have found out to be 2 volt, VB is standard for 0.7 volt for silicon. I should use not RB here, R Thevenin should be proper, R Thevenin I should write down R Thevenin. So, R Thevenin we have found out to be equal to 1.6 K. I am keeping all this in K and this voltage is in volt. So, that finally current expression will be coming in milliampere. So, 1.6 plus beta. Now, first case beta is 100. Let us take that 100 value, find out what is the current. RE is equal to 1.2 K into 1.2 K. So, this value will be coming to be 0.01059 milliampere, or it is equal to multiplied by 10 to the power 3 in order to write down in microampere. This is milliampere. So, 10 to the power 3 if we multiply, it will be 10.59 microampere. So, this 10.59 microampere current is flowing in the base. Now, corresponding collector current is beta times of IB, which is equal to beta value is 100 into 0.01059 milliampere, and that is equal to 1.059 milliampere. This is the first case when beta was 100. Now, second case when beta has risen to 300, let us find out that case. For that case when beta is equal to 300, here IB will be now changing, IB value will be 2 minus 0.7, only beta is changing, others are same. So, I write down for that value of beta 300 plus 1, here only I am just substituting, B Thevenin is 2, BB is 0.7, R Thevenin is 1.6 plus beta plus 1 is 300 plus 1 into RE is 1.2 K, and this value is coming out to be 0.003583, this much milliampere. So, that means equal to IB is now 3.583 microampere. So, now this different value of beta gives different IB. So, IC will be also different. This case IC is equal to beta times of IB equal to 300 into 0.003583, that will be equal to 1.075 milliampere. So, collector current was, in the first case collector current is 1.059 and first case collector current was 1.059 milliampere for beta is equal to 100. Now, when beta is 300, that is it is 3 times it is increased, the corresponding IC value we get is 1.075. Now, the first case IC was 1.059, this is not, sorry, this is 1.059, and now we have got 1.075 milliampere. So, now even though beta has increased 3 times, percentage value of increase if we see from 100 to 300, 200 times, 200% times increment of value of beta, that will be still giving a rise of IC, which is very marginal. That is, you can find out what is this change of del IC percentage, 1.059 minus 1.075, or if I do this other way round, that is 1.075 minus 1.059 by 1.075, that can be found out the percentage change, that will be coming to only 1.5%. When you change, the beta change is 200%, for 200% change of IB, still we get only 1.5% change of IC, and that is actually possible because in this design, if we cross check the values of R Thevenin and beta plus 1 into RE, the design specification to be met is R Thevenin should be less than, very less than beta plus 1 RE. Whether this is here, it must be there, because otherwise you would not have got such a marginal increment of IC. So, what is beta plus 1 into RE? Let us see. That is equal to, beta is first case say 100 plus 1 into RE is 1.2 K. So, that means 100, 1 into 1.2 is 121 kilo ohm, and the value of R Thevenin is 1.6 kilo ohm. So, R Thevenin and beta plus 1 RE if we compare, then you see one value is 1.6 K, other is 121 K, this whole term. So, it is very less than this. So, that means our design specification has been already met. That is why the IC is almost insensitive to beta, even though beta is changing so much, 200% change, but still we are not having corresponding high change of IC, and that is the beauty of this algorithm. So, this design scheme. So, here we are making it possible by this design criterion being satisfied. So, that is why we have the potential divider biasing scheme or voltage divider biasing scheme being used very popularly in transistor amplifiers, and we basically find its applications in amplifiers. Mostly this potential divider biasing scheme has advantages over the other biasing schemes that are already discussed, like the different variations of emitter bias, that is like collector emitter feedback bias. Then earlier we have also decided collector feedback bias only without the emitter resistance. Apart as compared to all these schemes, this voltage divider biasing scheme is still, I mean, it is edge over the others because of this flexibility in designing, that is we can design the biasing scheme very effectively by choosing properly the values of R1 and R2 to be quite small. R1 and R2 values, these actually have to be made small, so that you can maintain this condition R Thevenin, which is nothing but R1 parallel R2. So, that should be less than beta plus 1 Re. So, in the other case, for this example, if we even consider the change of beta as it is 300, new value of beta is 300, for that case still it will be maintained. So, that can be also checked if it will be even further made, because if beta is equal to 300, beta plus 1 is 301, 301 into 1.2 k, this value if we consider, it will be still higher as compared to this Thevenin resistance are 1.6 kilo ohm. So, both the cases if we see, then our design specification is met. That is why we have seen that this scheme is very effective from the point of view of beta change. So, here we are discussing the beta change predominantly because although there are other factors that may be present for change of the operating point, one being the leakage current change, that is the temperature at which we are working with that amplifier. If that temperature changes, suppose it is increasing, then corresponding value of IC naught will also increase, and that value of IC naught when increases, it is increasing the IC value. So, again the operating point shifting will be there, but still the effect of beta change actually very dominant than that IC naught change, and that is why we are mainly focusing on this change of IC due to beta. Now, this is the potential divider biasing scheme, and if we now consider the collector feedback bias scheme, suppose we have a scheme which is using the collector emitter feedback bias, that is this transistor having this 4.7 K, here 250 K, and this is fed back, this collector point with base is fed back to this 250 K resistance, and we have this 1.2 K. So, in this case VCC is 10 volt. So, here of course, we will be applying this input signal and we will be getting the output here, but with a capacitor it will be there, that means it will be having a coupling capacitor C2, and there also it will be having a coupling capacitor C1. Now, if we consider the DC circuit, then this will be removed. So, we can find out IC and VCE, find out ICQ and VCQ which is the value of IC and VC for the operating point. So, if for this particular case if we do using this expression for that beta into VCC minus VBE by RB, RB is this one, RC is this one and RE is this one. So, RB plus beta plus 1 into RC plus RE. So, putting these values we will be getting the ICQ. Similarly, VCQ, VCE can be found out by VCC minus, this is IC, this is IE and the IB is flowing in this loop. So, VCC minus IC plus IB, here this is IC plus IB current is flowing and this has to be taken care of, IC plus IB into 4.7 plus RE is 1.2. So, if we put these values, now we can find out IC first, beta is 90, putting the values of 90, 10 minus 0.7, all these values of RB is 250 plus beta plus 1 being 91, RC plus RE, RC is 4.7 and RE is 1.2. So, with these values we get finally IC is equal to 1.06 milliampere and VCEQ is equal to 3.68. We can check, you can check this calculation and this will be the operating point Q. So, the Q is written in the subscript, meaning that these are the values for that operating point condition, that is the DC condition, that is the Q point. So, this Q point you can find out on this load line where it will be either here or here or here, that is important, the location of the Q point. So, in this whole discussion we have now discussed about different biasing schemes. We have seen the potential divider biasing scheme has more flexibility as well as it is insensitive to beta after maintaining or till we maintain a particular design consideration with respect to the resistances being connected. So, till that limiting condition is satisfied, we can make the operating point insensitive to change in beta.